Hello, advanced placement students. In today's lesson, we're going to make the transition from regular Physics 30 course material into AP course material. However, before we can even get into our curriculum on advanced placement, electricity, and magnetism, there is a bunch of math that we need to be familiar with in order to handle a lot of the material from the actual AP curriculum. So before we get into the official curriculum for AP Physics C, Electricity, and Magnetism, I'm going to go through a series of about 8 lessons where I talk about vector math and also calculus that's going to be required again to let us go through the AP course material. So in today's lesson, we're going to start off by talking about vectors in 3 dimensions, which we don't have a whole lot of exposure to. Yes, there were some situations in the magnetic forces and fields unit when utilizing the third hand rule where we had to view things in 3 dimensions, but nothing as complicated as what we're going to get into in this lesson here. Okay, so let's start off with a 3-dimensional grid. Now, on this 3-dimensional grid, I have the x-axis that points down and towards the right, and we'll say down and towards the right is the positive x direction. You have the y-axis that points kind of like up and towards the right a little bit. We'll call that the positive y direction. And then directly vertically upward, we have the z direction, which I'll call the positive z direction. Now, on this graph, what I have is a vector whose tail is located at the origin, and it points to some kind of a point here where you have like the tip of the vector. Now, I don't know what that point is. Okay, I'm not clear as to like where the tip of the vector ends. Therefore, I'm going to have to do a little bit of clarifying with some lines on the graph to show you where that point is located, but just not quite yet. We're going to call this vector vector A. Now, what I'm interested in doing is I want a way to actually represent this vector in 3-dimensional space. And here's how we do it. We're going to represent the 3-dimensional vector as what we refer to as an ordered triple. An ordered triple is in the form A is equal to, open bracket, AX, comma, AY, comma, AZ, and then we close the bracket off. And in the ordered triple, in the brackets, those 3 values, AX, AY, and AZ, they all represent the vector components of this 3-dimensional vector. Or we can refer to it as a projection of a vector along the coordinate axis. And that's just a component. Now, we've done a lot of this back in Physics 20 and 30, taking vectors in 2 dimensions and calculating the x and y components, but a little bit tougher when you're looking at having this third axis, the z-axis, to deal with. Okay, so an ordered triple is basically in brackets, we have 3 values, and each distinct value is going to represent a component of the vector. Now, until we know where the tip of that vector ends off, there's no way we can actually identify what the vector components would be. So I'm going to draw a few lines on here that are going to help us identify where does that vector end at. So we'll start off with a horizontal line that is parallel to the x-axis. We'll do another line that is, I suppose it's horizontal if you look at the plane. In the actual diagram there, that grayish plane. That's parallel to the y-axis. And then we have another line that goes from like the intersection point of those 2 dashed lines all the way up to the tip of the vector. That identifies what the height of the vector would actually be, okay? Which is parallel to the z direction. Okay, now that I've done this, what I want to do is I want to identify what are the values AX, AY, and AZ. Okay, so let's go ahead and do this. Okay, so AX means it is the X component of this 3-dimensional vector. Okay, so the X component of this 3-dimensional vector is actually represented by this horizontal line here. Okay, so this horizontal line points towards the right. Okay, points towards the right here. And it does it by, so it points in the positive direction. So write down a plus here. And it does it by 1, 2, 3, 4 units in the positive x direction. Okay, how about the y component of this vector? So a, y. Well, the y component of this vector would actually be represented by this green line. So this green line would be a vector that starts in the x-axis and goes to this intersection point. So it points in this direction. So we have a, y. And it points in the negative y direction. So the negative y direction would be like down and towards the left. So it would be negative, and it does it by 1, 2, 3, 4 units. Okay, so it would be -4. Now, it might be kind of hard for you to see how these are actually the x and y components. So what I can do here is I'll just try to like make this vector stand out to you a little bit more. So the way I'm going to do this is I'm going to draw a line that goes from the origin and it moves over to this intersection point. Okay, so as best as I can, I'll make a line that goes from the origin to this intersection point. And then I'm going to shade in a triangular area to try to make the vector just stand out a little bit more. Okay, now hopefully now you can see a little bit better that the red line would represent the x component of this vector, and the green line would represent the y component of that vector. Okay, and again, the x component will be +4, so ax is +4, and the y component would be -4. Now, we need to identify, well, what's the z component? Okay, so the z component would just be what's the height of this vector from the intersection point to the tip of the vector we have here. Again, we're calling that vector A. Now, I can figure out where it hits the z-axis at if I take this purple line and I start it at the tip of the vector and draw a line parallel to that purple line at the bottom. So if I do that, I should get a line that looks something like this here. Okay, that's supposed to be parallel with that bottom one. Okay, so what that shows me is that what's the height of like this vector? Well, it would be in the positive z direction, and it would be 1, 2, 3, 4, 5 units up. So I'd say AZ would then be equal to +5. Now, to write that as an ordered triple, again, I could show the components here if you'd like. Okay, so again, that red dashed line represents the x component of vector A. The green line represents the y component of vector A. And then that blue line represents the z component of vector A. If we take those three together, we can describe this vector in three-dimensional space as this ordered triple. So that ordered triple would be A is equal to 4, comma, -4, comma, 5. So it's an interesting way of describing the vector. The way in which we describe the vector is we simply just write down the components. Maybe one way to think about it is like if you're trying to figure out how would I draw this vector if I was just given 4, -4, comma 5. Well, the way I would draw it is starting at the origin, I would go 4 units in the positive x direction. Then I would go 4 units in the negative y direction. And then I would go 5 units in the positive z direction. And then that's where your vector would end off at. And then you just draw a line that goes from like your starting position to where the vector finishes at. And that's how, again, we would represent this vector in three-dimensional notation. To calculate the magnitude of the vector, we do something that's pretty similar to how we would have done this in calculating the magnitude of a two-dimensional vector back in Physics 20. Okay, so the way to calculate it is This equation kind of looks like the Pythagorean theorem, but not quite, because you actually have too many terms. So if we only had like a two-dimensional vector, and I wanted to calculate the magnitude of the vector, so pretend for a second you don't have AZ, the magnitude would just be, you take the components, you would square them, find the sum of the squares, and then take the square root to figure out what the hypotenuse of the triangle is. And the hypotenuse of the triangle will just represent the length of the vector. Well, for three-dimensional notation, we use a similar procedure, except all we do is we add that z component squared at the very end. Therefore, the magnitude of a vector in three-dimensional notation would be take the x component squared, add the y component squared, add the z component squared, and take the square root. Now, I did box a number of this equation because there is a formula sheet that I did make available on D2L. I believe it's called like Math Formula Sheet, where I'm going to list all of the different numbered formulas as I go through this lesson here. Okay, so let's actually calculate that for the vector that we were looking at in the previous slide. So again, my ordered triplet is 4, negative 4, 5 meters. And again, we'll just assume that every grid line represents a meter off of that previous picture. So to calculate the magnitude, all you have to do is take those numbers and plug it into equation 1. So AX squared would be 4 meters, all squared, plus AY would be negative 4 meters, and we're going to square that, plus AZ, which is 5 meters, and we're also going to square that. If we calculate this to the nearest tenth of a meter, we would get the magnitude of that vector is equal to 7.5 meters. So that's how long vector A is from the origin to the tip of the vector. Now we're going to look at some mathematical operations that can be performed on these vectors. So one of the most simple things we can do is we can take a vector and we can multiply it by a scalar quantity. So first of all, let's say that C just represents a scalar constant. When I say a scalar constant, it just represents like a single numerical value. It could be like 1/2, it could be 4, it could be -2, just some kind of single numerical value. Now, what I want to do is I want to take that scalar constant and I want to multiply it by our vector A. Okay, so just take a scalar constant and multiply it by A. And then figure out, well, what would the product of that scalar and that vector be equal to? Well, if you take a scalar constant A, or C, and you multiply it by A, all you do is you just take the constant and multiply it by every single one of the components. So, for example, so up here we have our vector A is equal to 4, -4, 5. So let's say we want to multiply this vector by C. So the way I implement the C is just take the C and then multiply it by each of the components individually. So therefore, C times A would be equal to, as an ordered triplet, C times AX, comma, C times AY, comma, C times AZ. Okay, so multiplication of a scalar by a vector, all we do is we take each of those individual components in the order triplet and just multiply it by that scalar constant. Division's the same thing too. If we took like a vector and divided it by a scalar constant, we would just take every individual component and just divide by whatever that scalar constant value is equal to. Okay, so let's take an example. So we'll take our vector A, which again, as an ordered triplet, is 4, -4, 5. And then we'll take C, which is equal to 1/2. And what I want to do is I want to calculate the product C times the vector A. Okay, so all you have to do here is, if you want to go C times the vector A, okay, you would just take 1/2, and then you would just multiply it by every single term in the ordered triplet, each component. Therefore, c times a, so my first value would be 1/2 times 4. My second one, c times ay, would be 1/2 times -4. And then c times az would be 1/2 times 5. If we calculate this, then the multiplication of my scalar c times my vector a would be equal to, as an ordered triplet, 2, -2, 2.5, and that's expressed in meters. Now, how about adding or subtracting two vectors together? Okay, so I'm going to introduce a second vector. So we already have our first one, vector A, which is defined by the components AX, AY, and AZ. And then we're going to introduce a second vector, B, which is defined by the components BX, BY, and BZ. And what I want to do is I want to add or subtract these two different vectors together. And it turns out we've already done a little bit of this work before. We've had problems in physics 20 or physics 30 where we've had to calculate the net force on an object in the x direction or net force on an object in the y direction. And we figure out a net force by summing or adding different values together. And the way we did that is you add all the x components together individually, and you added all the y components together individually. And that's exactly what we're going to do here when we want to combine two vectors through addition or subtraction. We just add each distinct vector component together, and it's going to give us another ordered triplet. Now, we can write that down so it looks a little bit more complicated, although the equation looks more complicated than it actually is. So if you wanted to go vector A plus vector B, that would be equal to, as an ordered triplet, AX plus BX, comma, AY plus BY, comma, AZ plus BZ. Or if you wanted to subtract, so A minus B, that would be equal to AX minus BX, AY minus BY, and AZ minus BZ. So again, you just combine the X, Y, and Z components separately. Let's apply this to an actual physics problem though, a really simple physics problem. So it says an object moves from an initial position of A, which is 4, -4, 5, to B, 10, -3, -7 meters. So basically, the object is at the tip of vector 1, and I want to move it to the tip of vector number 2. And I want to calculate the displacement of the object in doing that. Now, going back to physics 20, displacement, delta D, is defined by the change in an object's position. Change in any kind of quantity is always a final position minus the initial position. Now, what we're doing here is we're moving the object from point A to point B. Therefore, XF would be B and XI would be A. So therefore, delta D would be equal to B subtract A. Okay, let's plug this in. So delta D is B subtract A. Therefore, in the ordered triple, the first value would be BX minus AX, which would be 10 minus 4, comma. The second value would be BY minus AY, so that would be -3 minus -4, comma. And the third value would be BZ minus AZ, which would be -7 minus 5 meters. Again, we keep the units on the outside of the brackets. This would then turn into delta D is equal to 6, 1, -12 meters, which basically means that if you want to go from the tip of vector A to the tip of vector B, you would need to go 6 units in the positive X direction, and then 1 unit in the positive Y direction, and then 12 units in the negative Z direction. Okay, so that would describe the displacement as a three-dimensional vector. Also, just wanted to point out that there's another way you can write down a difference between two vectors. So if we have B vector B minus vector A, we can also write it down as AB with an arrow on top. So the AB with an arrow on top just means we're going from A to B. Therefore, our change in position would be B minus A. Okay, now here's where the lesson gets a little more complicated. So we're going to introduce another special type of vector that is called a unit vector. Now, before even talking about what a unit vector is, the one key distinguishing thing between a regular vector, like the ones we had on this page here, like vector A, and a unit vector is that a unit vector has this little hat symbol on top of it. Now, because unit vectors are a little bit difficult to properly understand, I'm actually going to explain it from a two-dimensional perspective, just to again, just simplify it a little bit. Okay, so on the graph here, I have just a two-dimensional grid. So I have a y-axis, vertical y-axis, and a horizontal x-axis. And what I see here is I have a vector that starts at point A, the origin, and points to point B, which is located at coordinates 4, 3. And we're going to represent that with the vector A with an arrow pointing towards the right. So that's my regular old vector. Now, what exactly is a unit vector in relation to this? Well, first of all, let's just identify what the coordinates would be. So if you took this vector and you broke it into its components, so you'd have an x component that goes along the x-axis. So we could call that ax. And we have a y component that's parallel to the y-axis. So that would be ay. Okay, what I can see here is ax goes towards the right in the positive x direction by 4, so therefore it's positive 4. Ay, the y component, goes in the positive y direction by 3. And we can still write it as an ordered triple, it's just that there is no z component. So we write the z component as being equal to 0. Now, if you want to calculate the magnitude of this vector, so the way to calculate the magnitude is you would just do the sum of the squares of every value of the ordered triple. So this would be 4 meters squared plus 3 meters squared plus 0 squared, and then take the square root. This result shouldn't surprise you because this is actually a special triangle. So if AY here is 3 and AX is 4, this is a 3, 4, 5 triangle. So the magnitude of this vector A would be equal to 5. Okay, we still haven't talked about what a unit vector is just quite yet. So what I'm going to do is I'm going to start off by drawing what the unit vector would look like. Okay, so my unit vector, what I can see here is it starts at the same position as vector A. It points in the same direction as vector A, but it's not as long. So the question really is, well, how long is that unit vector? Well, let's try to provide a definition of what this is to begin with. Okay, first of all, a unit vector does not have any units to it. So as where vector A does have units in meters, a unit vector will not have any units at all. And there's a reason for this we'll get into in just a moment. So a unit vector points in the same direction as vector A. And I can see this. If you look at the diagram, let's kind of highlight it. Okay, vector A points up and towards the right, and the unit vector A also points up and towards the right, and it does it at the exact same angle. Okay, so it points in the same direction. Now, whenever you talk about like doing a calculation like per unit length or per unit time, what does that mean? Well, like per unit length or per unit time would be like per 1 meter of length, or it'd be like per 1 second of time. So that's actually going to define how long a unit vector is. A unit vector, so again, we use the symbol A hat for a unit vector, If I determine the magnitude of a unit vector has a length that's equal to 1. So on this graph here, this unit vector points in the same direction as vector A, except it only has a length that's equal to 1. What is this thing used to do? Well, we'll have to look at this more on the next slide, but the primary function of a unit vector is it's used only to describe what direction the vector is. It doesn't tell you how long vector A is. So we know vector A is 5 meters in length. The unit vector does not tell me that vector A is 5 meters in length, but it can at least tell me what the direction is, because it does point in the same direction as the unit vector. Okay, now what I want to do is I want to take that unit vector and I want to actually identify what are the different components of the unit vector. Okay, so to do this, I'm first of all going to identify an angle theta. So theta is going to be the angle between either the unit vector and the x-axis, or between the vector A and the x-axis. We'll call that theta. If I draw my components, I would have the x component of the unit vector points towards the right, and the y component of the unit vector points up. And what I want to do is I want to calculate what is the value. So again, here, let's pick a different pen color. Okay, so to fill in this ordered triplet, I need to know is what is the value of AX, the unit vector, the x component of the unit vector? What's the value of the y component of the unit vector? And what's the value of the z component of the unit vector? Well, we can already fill one of them in. Because the unit vector points in the same direction as my vector A, it does not have a z component to it. So we need to try to figure out what are the actual components. Or what are the components? Okay, here's how we're going to do this. Okay, so we'll use some basic trig. So I'll just show this over here. Okay, so what I'm going to say is cosine of theta would be equal to side adjacent over side hypotenuse. So side adjacent would be, we're going to take the magnitude of the unit vector A, and we're going to divide by the magnitude of the entire unit vector. Okay, now, what you know is that if we just take it a step further, so we go cosine of theta is equal to the magnitude of the unit vector AX. So the AX is the magnitude of the x component of the unit vector, divide by what's the magnitude of any unit vector? Well, it's just equal to 1. So what this would tell me is it would tell me that the magnitude of the x component of the unit vector would just be equal to cosine of theta. Now, the question is, well, what's cosine of theta equal to? Well, we actually have similar triangles here. So I'll kind of like highlight what the triangles are. So we have this small triangle that incorporates the unit vector, and we have a much larger triangle that incorporates the vector A and its components. So we can actually use the larger triangle to figure out what cos of theta would be equal to. So for the larger triangle, 3 would represent the side opposite, and 4 would represent the side adjacent. 5 would be the hypotenuse. Therefore, if I want to calculate what is AX, AX would just be equal to cosine of theta. So you have AX would be equal to, so cosine of theta is a ratio of sides. So it'd be side adjacent, which is 4, divided by side hypotenuse, which is 5. Therefore, the x component of this unit vector would be 4 over 5. And you can see right here why the unit vector doesn't have any units, because you just be taking the side lengths and dividing. Therefore, the meters units would just cancel each other off. Well, how about the y component? Well, the y component would be sine theta would be equal to side opposite on the small triangle, which is the magnitude of the y component of the unit vector, divide by the magnitude of the unit vector itself. Now, once again, the magnitude of the unit vector is equal to 1, which is just going to tell me that ay would be equal to, oh, not ay with the arrow, ay with a hat. We're looking at the magnitude of the unit vector. Okay, so that's just going to be equal to sine theta. Okay, so what's sine theta equal to? Opposite over adjacent. So side opposite is 3, opposite over hypotenuse. So you'd have opposite over hypotenuse, so that'd be 3 over 5. Therefore, the unit vector would have an x component of 4 over 5, and it's positive because it points in the positive x direction. It would have a y component that's positive 3 over 5 because that ay also points in the positive y direction, and it doesn't have a z component at all. So that's how I would write down the unit vector as an ordered triple. Okay. Yes, just a reminder, a unit vector has a magnitude that's equal to 1. And for this two-dimensional vector, for the unit vector, the x component of the unit vector was cos of theta, the y component of the unit vector is sine of theta, and the z component was 0. And if we write this down correctly, we have a is equal to, as an ordered triple, 4 over 5, 3 over 5, and 0. So the key thing about those two vectors is that the vector a and the unit vector is that they have the same direction. Okay, if you actually tried to sketch those vectors, you would end up getting the same direction, but they don't have the same magnitude. The unit vector has a magnitude that's equal to 1. Okay, so you might be wondering, okay, cool. So you have this special thing called a unit vector. It points in the same direction as my other vector. Its length is equal to 1, but like, what's the point of this thing? Like why am I actually interested in it? Okay, so I'll try to clarify this a bit on the next slide here. This is where it gets like a little bit, continues to get more complicated. Okay, so a unit vector A, again, we know it's a unit vector because it has that hat on top of it, is essentially a factor that will take a magnitude of a vector and it will actually turn it into a vector that has direction. And the way it does this is we take the magnitude of the vector and we multiply by the unit vector. Now realize everything I just stated in that sentence is exceptionally confusing. So let's just try to take that statement and turn it into a mathematical statement. Okay, so what this is going to tell me is that, let's say that for vector A, you just knew what its magnitude was. Okay, so let's write down MAG for the magnitude. Now, if you knew the magnitude of a vector and you knew what the unit vector is, what the unit vector does is the unit vector only tells you direction, but not magnitude. So let's look at it right here. So this vector, absolute value of A, tells you magnitude, but not direction. The unit vector tells you direction, but it does not tell you the magnitude of vector A. Now, what I can do is if I take the magnitude of vector A and multiply by the unit vector, I can actually combine magnitude and direction together. And then what you end up getting is you get vector A, which has both magnitude and it has direction. So if you take the magnitude of a vector and you multiply by the unit vector just tells you the direction of that vector. We can actually then form a vector where we could determine both the magnitude and direction. So that's what this thing does. A unit vector is kind of like a conversion factor that can take the magnitude of a vector, multiply it, and it actually give you what the vector is, incorporating both its magnitude and direction. Okay, let's try to see if we can support this based on the work from the previous slide. Okay, so let's try to calculate what A is. Now, from the previous slide, my vector A, so let's go back here for a moment, that's this really long vector. It has a magnitude that's equal to 5. Okay, so I have a vector magnitude of equal to 5. Now, we multiply by the unit vector, which we determined. Okay, the unit vector is an ordered triple, can be represented as 4 over 5, 3 over 5, and 0. So if we multiply those two together, now what you're doing is you're multiplying a scalar by a vector. So we take this 5 and we multiply it by each of the components individually. Okay, so the 5 is magnitude. The unit vector is just direction, but not magnitude. It's my conversion factor that's going to take magnitude and form a complete vector. Okay, so if I multiply the scalar by the vector, I would then have 5 times 4/5, where the 5s would cancel off, 5 times 3/5, where the 5s would cancel off, and then 5 times 0, which is 0. And then this would give me vector A would have, as an ordered triple, would be 4, 3, 0. And if you go back to the previous slide, that was indeed that vector in three-dimensional notation. So once again, like one significance of a unit vector, and there's other reasons we use them too, is that if you take the magnitude of a vector, multiply by its unit vector, you can actually form the vector where I have its direction and have its magnitude represented by this ordered triple. Okay, a little bit confusing as to like what it's used to do, but like that's one reason we use unit vectors. It's a way of just taking magnitude of a vector, and then by multiplying by the unit vector, we can actually get the vector that incorporates both magnitude and direction. Now, let's say that we want to calculate the value of a unit vector, and we can do that by manipulating this equation. So this equation is A, the vector A, is equal to the magnitude of vector A times the unit vector A. I just realized I said A a lot of times. Okay, I want to get the unit vector isolated, so get A hat by itself. Okay, divide both sides by the magnitude of vector A, and you'd have A hat would be equal to the vector A divided by the magnitude of vector A. Now, if we expand this, you can treat this guy as a scalar. So if you take a vector and divide by a scalar, it's actually the same thing as taking a vector and multiplying by a scalar. So what you would do is you take every single component in the ordered triple and you just divide by the value of the scalar. Okay, so let's go back to our very first vector that we started off with. So vector A as an ordered triple is 4, -4, 5. And let's say we want to actually figure out what the unit vector is for that vector. Okay, so that's the vector from slide number 1. Now, from that vector, in example 1, we determine the magnitude of the vector is 7.5 meters. So what I'm going to do is I'm going to calculate the unit vector by taking AX, AY, and AZ. AX, AY, AZ, and I'm going to divide by the magnitude of that vector A. Okay, so A hat is vector A divided by the magnitude of vector A. So that's going to be equal to 4 divided by 7.5, comma, -4 divided by 7.5, comma, 5 divided by 7.5. And then this would give me A hat is equal to 0.53, comma, -0.53, comma, 0.67. Okay, now I'll show you what this looks like visually in a second, but I just wanted to point out once again that a unit vector must have a magnitude of 1. So if you want to calculate the magnitude of this unit vector, this would be equal to 0.53 squared plus negative 0.53 squared plus 0.67 squared. Take the square root of that. And if you want to go ahead and confirm that in your calculator, you can, but it would show you that the value is equal to 1. Now, let's try to see what this visually would look like. So let's go all the way back to the first slide here, okay? So all the way back. So I'm just going to erase all this junk off of here because it's a little bit too much to look at right now. Okay, so here's my vector A. Okay, and we can see what direction it points in. Now my unit vector, I believe, was it, I think it was 0.53, negative 0.53, and 0.67. I just want to double check that. Okay, let's just see. Is that the unit vector we got? Yeah, 0.53, negative 0.53, 0.67. Okay, now, let's say you want to sketch this unit vector. So what I could do is, like, if I made like an actual like Cartesian grid here. So let's say this is like the Z direction. This is the X direction. This is the Y direction. Okay, and we'll just label, let's say this is 1. So that's positive 1. We'll say that's positive 1. We'll say this is positive 1. Okay, so the way I would attempt to like draw this thing would be starting at the origin. I'd first go 0.53 units to the right. So that might be like right here. Okay, it's just halfway there. And then in the Y direction, I would then go up in the Y direction by negative 0.53. So that would be like somewhere going, well, I have to extend it in the opposite direction to see this. So let's make this guy go down here. We'll say if that's 1, maybe like negative 1's right here. Okay, so then I would then go in the negative Y direction by this amount. So maybe it ends up like right here. And in the Z direction, we want to go up by 0.67. So 0.67 looks like a length of about maybe about like here. So we go like up by 0.67. So and then that's too high. I think let's try that again. It's hard. I'm just trying to translate what 0.67 would look like. I think like here, this would be this is about like 0.67. So I need to make this line go up by this small amount here. So it'd actually probably like end up like right here. Yeah, this would be like really hard to see. So maybe go from here up to there, here up to there. So maybe it's about here. So the way you draw the unit vector is it would have to end at like this point here. And then you just draw a line from like start to finish. So you just draw like a line that goes like this. Again, this is like super hard to draw. I mean, you could try to do the same thing on this grid here to show it. Now, the key thing is the unit vector should point in the same direction as my vector. So if I went 0.5 to the right, that's probably about like right here. And then I went like 0.5 in the negative Y direction, it's probably about right here. And if you went up by 0.67, then you're probably like up to right there. And then if you draw a line from start to finish, let's do it in like yellow here. Start to finish, then that unit vector A points in the same direction as vector A. So again, the only thing that the unit vector tells you is it tells you what direction the vector points, but it does not tell you how long the vector is. Okay, now let's go on just a couple steps further. Now it turns out there are actually a couple of special unit vectors, and there's a notation that incorporates these unit vectors. So let's go back to a three-dimensional grid. And on this three-dimensional grid, let's just label it quickly. So we'll say this is the x-axis, we'll say that's the y-axis, this is the z-axis. And I'm going to start off by drawing a unit vector, which I'm going to call unit vector I. Unit vector I starts at the origin and it goes to +1 on the x-axis. Now, if I want to write that unit vector as an ordered triple, it will be written as 1, 0, 0. Now, why does it look like that? Well, because the x component of vector I just points in the positive x direction by 1. What are the x and the y and z components of this vector? There are none, okay? Because there's no part of this vector that points in the y or the z direction. Now, we also have a special unit vector that we call unit vector j. Now, unit vector j starts at the origin and it just goes to +1 in the y direction. So if I wrote that one as an ordered triple, it would then be 0, 1, 0. So this one doesn't have any x component, okay? There's no part of the vector along the x-axis. It has a y component that points in the positive y direction by exactly 1. And it does not have a z component to it. And then we have the special unit vector k, which doesn't have an x or a y component, but it has a z component because it points in the z direction by 1. And again, these are all unit vectors because if you calculated the magnitude of every single one of them, they would be equal to 1. Okay, so the unit vector I only has an x component, the unit vector j has only a y component, and the unit vector k has only a z component to it. Now, you might be wondering, okay, cool, there's like 3 special unit vectors, what's the point of these? Well, this actually allows us to express vectors in an alternate notation. So far in this lesson, the way we've been expressing three-dimensional vectors is as an ordered triplet. But it turns out in higher level physics courses or engineering courses, we like to express three-dimensional vectors in something called Cartesian vector notation. And the Cartesian vector notation makes use of these 3 special unit vectors. Okay, so let's say we have an ordered triple A, which has an x component ax, a y component ay, and a z component az. It can be expressed in terms of the special unit vectors as follows. So I have A is equal to ax times the unit vector I plus ay times the unit vector j plus az times the unit vector k. Okay, let me give you an example of what this might look like. So let's say I had an ordered triple vector that was maybe like something like, I'll make up just some numbers here. So we'll say it's like 2, I'll say -9, and I'll say +5. 2, 9, +5. Okay, so this 2 is ax, that -9 is ay, and this 5 is az. Now, if I wrote it in this format here, the Cartesian vector notation, what it would look like is you would have A is equal to 2I minus 9J plus 5 times K. Now, the one thing I want to point out just for explaining how this works is that you'll remember the special unit vector I only has an x component, therefore it's attached to the x component of vector A. Special unit vector J only has a y component, therefore it's connected to the y component of this vector. And special unit vector K only has a z component, so it's connected to the z component of this vector. Now, I want to show you why this actually works. Okay, so I'm going to take this this vector expressed in, so this here is what we call Cartesian vector notation, and I'm going to take it and I'm going to show you how I can get an ordered triple. Okay, so here's how it would work out. So this would be A would be equal to 2 times I. What's a special unit vector at I? It's an ordered triple, 1, 0, 0. Okay, and then we're going to subtract 9, multiply by the special unit vector j, which is 0, 1, 0. And then we're going to add this 5, multiply by the special unit vector k, which is 0, 0, 1. Now, the way to properly expand this is what we're doing is we're taking a scalar and we're multiplying it by a vector. Okay, so these ones are scalars. We're going to multiply them by the special unit vector. So we take each scalar and multiply by each part of the vector. Okay, so this would then give you A would be equal to, so the first one would be 2, 0, 0. Then we take the negative 9 and multiply it by all three parts of the special unit vector j. So that would be plus 0, negative 9, 0, and then plus, take this 5 and multiply it by everyone here. So it would be 0, 0, 5. And now look what happens. We're now adding three vectors together. When you add or subtract vectors together, you only combine their components. So when I combine these together, the first value in the ordered triple would just be 2 plus 0 plus 0. So that would just be equal to 2. The second value in the ordered triplet would be 0 plus negative 9 plus 0. That's combining my y components. So that would be negative 9. And then the third value in the ordered triplet would be combined the z component. So 0 plus 5, which would just be equal to 5. So all this is an alternate way of expressing a vector in three-dimensional notation, but it is more common, okay, in like later physics and engineering courses. Okay, I'm going to erase all this so we can actually see the example, and this is going to finish the lesson off. Okay, it says write the following 3D vectors in Cartesian vector notation. So these three vectors are all written in as an ordered triples, okay, or triplets, and we want to write them in Cartesian vector notation. Okay, so all we have to do is we just have to replace the values of ax, ay, and az. Okay, and then we just leave the unit vectors alone. Okay, we leave the special unit vectors as I, j, and k. Therefore, the first one would be, now one difference is that we put it in Cartesian vector notation instead of using kind of like these brackets that are a bit more like solid lines. We use like an open, like kind of like curly bracket. So this vector can be written in Cartesian vector notation as 4i minus 4j plus 4k. Close the bracket on the outside, we write down what the unit is. The unit would be meters. For vector b, this would be 10i minus 3j minus 7k. Close the brackets, and it's expressed in units of meters. Now, this one doesn't have a z component to it. So if you take a z component and multiply by the special unit vector k, it's just going to get rid of it. Okay, so vector c in Cartesian vector notation would be 4i plus 3j. Close the bracket off, and we have units of meters. Okay, that's it for this first introductory math lesson. And again, it covered how to write vectors in 3D notation as ordered triples. We talked about how to calculate the magnitude of a three-dimensional vector, how to multiply a scalar by a three-dimensional vector, how to add or subtract three-dimensional vectors. Then we got into the more confusing discussion of like how the unit vectors work. And then we looked at some special unit vectors, which gave us an alternate way to write three-dimensional vectors in what we call Cartesian vector notation. Now, really for the unit vectors, you just need to practice like utilizing them. And the way I'm going to have you practice in this kind of like pre-unit of study is for each math lesson, I have a D2L quiz that typically consists of about 5 questions. So for this first lesson, there's a D2L quiz, which I believe is called 3D vectors. Okay, so it's going to cover everything that we just looked at within this lesson. The one major difference between like these D2L quizzes and the other ones from Physics 30 is that I give you unlimited attempts on them. So the Physics 30 ones, you only had 3 attempts. These ones, you have unlimited attempts. And these D2L quizzes, which are going to prep you for the math required to do AP Physics C, will count for something around about, I don't know, maybe 5 to 10% of your overall grade that I record for Physics AP. So they are something that does need to be done. Because like I said, like the quiz is the way to reinforce the material. And once you have the material reinforced, then we can actually start to do the actual course content from Physics C, electricity, and magnetism. Okay, and in the next lesson, you'll notice here that we did not talk about what happens when you multiply a vector by a vector. Well, that's because it's a lot harder than adding or subtracting vectors. And there's actually 2 different ways we can multiply them. And that's what we're going to get into in the next lesson. And I will talk to you then.